9.4 sequences. You've been dealing with sequences for like a really long time, probably.
Just didn't know it.
A sequence is just a fancy word, basically. Actually, it's not even a fancy word. It is the word for an ordered progression of numbers. Some examples of this, like 5, 10, 15, 20, 25. Pattern, that's what I was thinking.
Pattern.
A sequence is just a pattern, basically. And so these actually kind of are different examples of how we can write these things. So like, you can just write it out. This is 5 things long. Or we've got this sequence, and then...
Anytime you see the ... and this stuff, that means keep going forever and ever.
Right, so this is saying we could keep going past 32, and then this is saying to find any term in our sequence, we could use this formula 2 to the k, and then even after that, it would also keep going. This is saying that our sequence is 1 over k for values of k, 1, 2, 3,
right,
and so on.
And then we just keep going. I mean, the only person I know of that can count to infinity...
Yeah.
Chuck Norris.
I've heard that before.
He
about
did it
him.
twice.
Wow, twice?
Yeah.
That's impressive.
I know, right?
And then this is going to be a common thing we'll see. There's little curly brackets around this, which we...
Fancy brackets.
Which we know, usually that means some kind of a sequence or set of numbers. And then we use these subscripts to talk about the term. So like this is our first term, our second term, our third term. It keeps going until we get to some kth term.
Yeah, which would be whatever term you're on.
Yeah, and then it could keep going after that. And sometimes we just abbreviate that type of sequence A with a subscript of K. And when we do that, we're talking about the whole sequence.
Not just part of it.
Yeah.
Right.
So vocabulary, we have a finite sequence, has a countable number of terms. Countable as in, like, you could count
number of fingers and toes.
Yeah, so that's like this first one. We can count, this has 5 terms, so it's a finite sequence. And on the other side of that is an infinite sequence, has infinitely many terms, so you couldn't sit there and count it. So
Chuck Norris could.
Yeah, only if you're Chuck Norris. And so these 3, because they have the ... which are ellipses.
I don't know what those are called.
Something like that.
Yeah, some fancy.
And it means they keep going forever, so they are called infinite sequences.
Mm-hmm.
So there's 2 different ways that our book talks about defining sequences. One of them is explicitly. And typically the word explicitly means like obvious.
Right. Like I want this term right here, right now.
Right.
Like I want this specific piece of information without doing any other work. I just want to know what this value is.
Right. So in this problem, this example, we have a sequence here. This is considered defined explicitly because no matter what term you want, you just plug in that number for k and it tells you what that term is. So it asks us for the first 6 terms. So if I want the first term, then I'm finding a of 1. That means the first term, and I plug in a 1 here.
Everywhere you see k, you put a 1 in.
Yeah.
Yeah.
And so 1 minus 1 is 0. So our first term is 0. Then,
six of those? Oh, you're going to write a bunch.
Maybe. We'll see what happens. So now I plug in 2. So 2 squared is 4. Minus 1 is 3.
That's 3.
So 3 squared minus 1 is...
8. It's 9 minus 1, it's 8.
Okay.
Well, I don't even know why you hesitated. I have never been wrong on this stuff. That's going to be 15. BT dubs.
Okay.
Go ahead, work it out. 16 minus 1.
Now there is a pattern that's happening here, I believe. Well, there has to be. It's a sequence, but like a pattern that we can actually know. Like we're adding 3 to get between here, adding 5 to get here, adding 7 to get here. I must need to add the next odd number, which is
25
9.
minus 1, which is 24. Everybody knows that.
Yeah, so it may or may not be worth it for you to spend your time trying to figure out the pattern.
36 minus 1 is 35.
Yeah. Okay, so this is...
Hey, look, there's a pattern.
There's a... Here are the first 6 terms.
They go up by increasing numbers of odds.
Increasing odd numbers, right. Each time you're adding
Shut
the next bigger odd number. So, but that would be really difficult for us to write out all the way to the 100th term.
Yeah,
so
who wants to do that?
It's really nice that they gave us this formula. So we put in A100, so that's 100 squared minus 1, which is 10,000 minus 1.
999,999.
No, wait, I have the decimal in the wrong spot. I don't know if you said it right or not, but 9999.
Well, I said something like that,
yeah.
So that's got to work, right?
Yeah, so all of these are our answers.
And it's explicit because if I want to know the 15,000th term,
whatever term you want,
just
you got
plug it
it.
in.
Explicitly. It's obvious.
Mm-hmm.
Like, explicitly.
It's
Example
totes
2,
obvi.
the other way is to define recursively, and if you're in computer science, you may have heard this word before.
Maybe you have.
My husband, who's a computer science person, is not fond of this word, and I, as a math person, sometimes recursion is not fun. But this really isn't that bad for sequences, because what happens is they'll tell you like the first term, or maybe even the first and second term.
They might get you started here.
Yeah, and then they tell you how to find all the rest of the terms using a term you already know.
Right, like I can't, like if you were to ask me to find the 100th term of this one,
That'd be super difficult.
I just couldn't do it because I would need to know 99 first, but then I would need 98.
But they do actually ask us for the 100th term, so we're gonna have to figure out.
For the love of Pete!
So let's just start off though with the first six terms. And so basically recursion is plugging things in backwards.
Yeah.
Like using what you already know to get
find,
something new.
Yeah, use what you know to find what you're being asked.
Okay, so B1 equals 3.
You do that while I play 2048. So
okay, B2.
Let me know when you get there.
And if you plug in a 3 everywhere that
Hold
n
on,
is, you can play, just don't disturb us over here on the video. Okay, so n is 2, so we're saying b of 2 minus 1 plus 2. So that's really saying b of 1 plus 2, and we know that b of 1 is 3. So we're really doing 3 plus 2, and that's 5. That's our next term. Right. The cool thing about this is if you can wrap your head around it, what are we doing each time to get the next number?
Adding 2.
Adding 2 to the previous number. So b3 is simply 7. B4.
No, after. After B3, not before.
Is 9. B5 is 11.
What is that?
Your computer keeps like lagging on me.
Don't blame my computer
totally
for your issues.
Here's the first 6 terms, and so as Mr. Hazelwood pointed out, we don't really want to sit here and do this until you get to the 100th term.
No, that's
There's got to be a better way.
There's got to be.
Let me just write out what we got here. 3, 5, 7.
I think I see an
9,
explicit formula.
11, 13. We've got odd numbers starting with 3. So how could we write a formula for this? We want it to start with 3, but then we're adding 2 every single time.
2n.
So that's 2n.
Let's start with 2n and we can modify as needed.
Okay. So
check it. 2
so if
times,
I plug in 1,
right.
Do I get 3? No, I don't.
No, because that makes it 2 plus 3, which is 5.
Right.
So what if we go 2n plus 1?
And then put that in parentheses? You mean minus 1?
No. Just erase the 3 and put a plus 1 there. Because we were 2 over. So
right, we're 2 over.
So what if I put a 2n plus 1? Now Mrs. Stevenson is thinking of a different pattern, and that's the beauty with these. There are
different ways of thinking of it. So if you say, hey, we're starting with 3 and then we've got 2n, and you try that for 1 and you got 5. So he's saying instead of having 3, let's subtract 2 and get 1. Well, that's going to give us what we want.
Yeah. Now, Mrs. Stevenson was thinking of something different, and that's perfect. That's why these problems are kind of fun.
Yeah, and also can be frustrating.
Yeah. So what were you thinking of, Mrs. Stevenson?
I was thinking of like basically what you would do is in parentheses you would do an n-1 situation. Because when you plug in 1 here, now I've got 0. 0 times 2 is 3. 0. And
so look, both of those work. That's the cool thing.
Okay, so to get the 100th term, we need to plug in to one of these 2 formulas, 100.
A hundy.
A Hyundai?
No.
Like a car?
No, a hundy, like 100, like a cool way.
201.
Like if I got a hundy, I got $100. You know, a hundy.
201. And if I do it this way, if I do it this way, I have 100 minus 1 times 2 plus 3. That
That's
also
just
works
99.
out. 99 times 2 is 198 plus 3 is 201.
There you go. Chitty chitty bang bang.
Or if you want to, just keep adding until you get to the 100th term.
You think you're as good as Chuck Norris?
Go for
Knock your
it.
socks off.